Hello, welcome to Cardinal Science. Today we're working through specification points 1.3 to 1.7 of the Edexcel IGCSE Chemistry 2017 specification. For specification points 1.5 to 1.7, you'll notice that there's a big C next to each one. This indicates that it's part of the triple science specification, which means if you are only doing double science, you don't need to do these. Right, we're starting with point 1.4 today. It makes more sense this way. So, specification point 1.4 says, know what is meant by the terms solvent, solute, solution, and saturated solution. I've got the four definitions up here for you. So your solvent is the liquid in which a solute is dissolved. So that's your water or your alcohol typically. The solute is the solid that will be dissolved in the solvent. So that's the sugar you put in your tea. And the solution is the mixture of those two things together. Now, when you keep adding a solute to a solvent, eventually you'll hit the point where you can't dissolve any more of that solute in that solvent. And at that point, the solution that's made is referred to as a saturated solution. It can't hold any more of the solute. Okay, so let's illustrate this then. Let's say for a moment that you're the huge cockroach alien from Men in Black, the one who was obsessed with sugary water. Let's say you're going to make him his favourite drink. His favourite drink is a sugar solution. A solution is made when a solute is dissolved in a solvent, if you remember. So in this case, you would take some sugar, the solute, and add it to the water, the solvent. When these two things are mixed together, we therefore call it a solution. And if you kept on adding sugar and stirring it and adding and stirring and adding and stirring, eventually you'd get to the point where no more sugar dissolved in that water. You'd see sugar at the bottom of the cup. And at that point, you would have a saturated sugar solution. Specification point 1.3. Experiments with dilution and diffusion. So for this one, you have to understand how the results of experiments involving the dilution of coloured solutions and diffusion of gases can be explained. So there are two parts to this. We'll start with diffusion of gases. Here, on the left, we have bromine gas, which is Br2, in a container. At the moment, all of the bromine molecules are trapped in the bottom half of the container, as you can see. There's a thin piece of plastic there holding it at the bottom. Now, since there are lots of bromine molecules close together in that lower part of the container, the colour of the gas is quite dark. The upper half currently contains no bromine, but contains atmospheric gases, so oxygen, carbon dioxide, nitrogen, and a few other things. Now, when I remove the piece of plastic, the bromine molecules will be able to move up into the top half of the container. The particles are moving randomly, but over time they will spread out evenly throughout the container. Now that the particles are further apart and separated from each other by the atmospheric gases, the colour is much paler, as you can see on the right there. A similar situation occurs when coloured solutions are diluted, i.e. when they have water added to them. Here you can see some potassium permanganate crystals. They're a really brilliant purple colour. These are the solute in this example. When these are dissolved in water, the solvent, they form a dark purple solution, as you can see on the right. The potassium permanganate molecules move randomly in the solution and are evenly spread. If, for example, these containers are, say, 1 litre, and we remove 100 millilitres and put that into a new container, and then fill up the new container with water, we'll see that as the water mixes with the solution, it becomes lighter. Why does this happen? Right, I've illustrated the process here then. On the left, you've got the undissolved potassium permanganate. Then moving to the right, you've got the concentrated solution that's all dark. We've then removed 100 millilitres, third from the left, okay? And then we've re-added some water to fill it up to the same volume. And as you can see, the colour has become slightly less strong, okay? Now, the molecules that were in the 100 milliliter portion of the solution have now been mixed with water, and they're therefore much more spread out, which makes the colour paler. This is the same concept that you apply if you've accidentally made a glass of squash too strong. You pour some out and fill up with more water. This makes it paler in colour and weaker in taste because the squash molecules, the flavour in there, is now further apart and separated by water molecules. And of course, you can continue this process and dilute it and dilute it and dilute it until eventually it would be almost as pale as pure water. Specification point 1.5c. Know what is meant by the term solubility in the units grams per 100 grams of solvent. Right, the first thing to cover in this is to point out that when we refer to solvents, we'll generally be referring to volumes, i.e. millilitres or litres. For water, 1 milliliter is equivalent to 1 gram. So essentially we're talking about how many grams of solute will be able to dissolve in 100 millilitres of water. This value will be different for other solvents. So, for example, if 10 grams is the maximum amount of solute that dissolves in 100 millilitres of solvent before it becomes saturated, then its solubility is 10 grams per 100 millilitres, or 10 grams per 100 grams. Now, this diagram illustrates the construction of a saturated solution. So on the left you have undissolved potassium permanganate crystals in water. In the second stage you have the dissolved crystals. In the third you're adding some extra crystals, and as you can see, only 3 of the 4 have dissolved, and that fourth one is remaining out of solution. Therefore, that solution on the right in the dark purple is saturated, and we could just filter out that final crystal to remove it. Right, now, further illustration then. So if you had 12 grams as the maximum amount of solute that could dissolve in 100 ml of solvent before it became a saturated solution, then its solubility would be 12 grams per 100 ml, or 12 grams per 100 grams for water. And likewise, slightly more complicated though, if you had 10 grams as the maximum amount of solute that dissolves in 50 milliliters of solvent before it became saturated, then its solubility would be 20 grams per 100 milliliters, or 20 grams per 100 grams if the solvent is water. Notice that we had to double the amount of grams then, because we had only 50 milliliters of solvent rather than 100. Specification point 1.6c. Understand how to plot and interpret solubility curves. So a solubility curve is a graph that represents the solubility of a solute at different temperatures, and this is in the same units as we just used, grams per 100 ml or grams per 100 grams. As you can see, solubility generally increases with temperature. We've got 3 different solids here in this graph, and if we were to look, for example, at solid B, which is in the red, so we go to 20 degrees and we could read up and see that the solubility at 20 degrees is approximately 80 grams per 100 ml. Therefore, if we continue and say we've heated it up to 100 now, we would read across and figure out that the solubility at that temperature is about 320 grams per 100 ml. 1.7c, practical. Investigate the solubility of a solid in water at a specific temperature. You're going to have to be very clear here about the conditions that you're going to use in this investigation. So, set your water bath to a specific temperature, choosing something reasonable, somewhere between say 40 and 80 degrees. Measure out a specific volume of water. 100 milliliters would be easiest, but a multiple of this would also be acceptable. Place your beaker containing that water in the water bath and monitor the temperature with a thermometer until it has reached the temperature of the water bath. Then, add a known mass of the solid, the solute, and stir until it has dissolved. Repeat this step by adding known masses of that solute and stirring until no more dissolves. Once you've hit this point, your solution is now saturated. So now we've covered the content, that only leaves one thing to discuss. How was this stuff examined? Common 1 or 2 mark questions on this topic involve defining solute, solvent, and solution, or identifying the correct definitions given a table. Trickier questions will involve describing the findings from the dilution and diffusion experiments. You could be asked to interpret a solubility curve by, for example, reading off the graph and stating the solubility for a given temperature. If you look at this graph, we've got solubility curves for 3 different solids, A, B, and C. To figure out the solubility at any given temperature, we just need to read the graph. I'll show you here how to do it for 80 degrees C. We read up vertically from 80 degrees on the x-axis and you can see where it crosses the three different plots. Then we read along horizontally until we reach the y-axis, and we read off the values. So for solid C in green, we get approximately 85 grams per 100 ml. For solid A in blue, we get about 180 grams per 100 ml, and for solid B, we get about 260. A quite common question on this topic will involve you undertaking some simple maths to figure out how much solute is dissolved in a solution. When a solution is boiled, the solvent evaporates and any solutes dissolved are left behind. Therefore, if we want to figure out how much solute is dissolved in a solution, we just need to measure the volume of the solution and then boil it away. This will leave the dissolved solute behind. If we know the mass of the solute left behind, then we can figure out the solubility. So, in this case, for example, we've boiled off 100 milliliters of solvent in an evaporating dish or crucible. To figure out the mass of the solute, we need to subtract the mass of the crucible from the combined mass of the crucible and the solute. In this case, that is 112 grams, take away 100 grams, which leaves us with 12 grams of solute. So, we had 12 grams in the solution. If the solution was saturated, we could say that the solubility is therefore 12 grams per 100 ml, or 12 grams per 100 grams if it was water. Finally, you could be asked to describe an experiment to ascertain the solubility of a solid at a specific temperature, as I just discussed in previous slides. This will be a 6-mark question where you need to detail every step in specific detail. I hope you found this video helpful. If you liked the video and would like to see more videos like this, please like and subscribe. You should see the button below. If you have any thoughts or questions, please comment and I'll be sure to respond.